LinkedIn, it's Ali G. This video is about what IO checkout is. So, when you put in a new system and it is automated, typically that's done with a PLC. So you have some sort of, a control cabinet, and then, maybe you do or didn't, put it in the same cabinet as all your power to do like all your motors. But when you put in new processes, you have to, when you first start it up, it check, that it was really wired right. And that's called IO checkout. And it's not just you checking IO, because you will be checking everything involved in your process. So if you have, things that require power, you're going to have to put full power to those. For example, motors is the big one, right? So although I've seen 480 valves, but that's weird. So I have this crazy hair because under this is hard hat hair. So pro tip, carry a hat with you if you wear a hard hat, because hard hats are not nice to hair. Moving on, IO checkout. There's a physical aspect in the beginning where we're actually checking wiring, right? Like we'll check, with all the power off, we'll check all the motors and that they're all wired for whatever voltage we think that they're supposed to be wired for. So if it's all 480, then it's all 480. If it's all 230, it's all 230. That's the normal three-phase in America, is 230 or 480. So usually it's all one or all the other. There can be mixes, of course, but that's a typical setup. It's like you're going to do IO checkout, and now you're going to check all the motors that they're all 480 or they're all 230. And then when you've done that, you actually will bump all those motors, you'll bump all the motors and check direction. So there's an arrow on there, and you can see, even with the fan, goes the same direction. So you can check, if you can see the impeller, great. If you can't, and you need to look at like the fan on the motor itself. Like you need to check that the motors are going the right direction, unless they're reversing motors. And I don't have as much experience with reversing motors. I normally just have to turn on motors that are like one direction, like a pump or a blower. And so, once we get the phases right, and that, by the way, that's how you reverse a motor is, if, like, let's say we check a motor and it's the wrong direction, okay? You say, hey, stop it, and then you ask somebody to go rewire 2 of the 3 legs. It doesn't matter. And, let's say it's all 480, so there's like brown, orange, yellow down there. That's the NEC colors for 480, 3-phase. Let's say you just swap any 2. I don't know why that works. Like, that's above my pay grade. I am a chemical engineer. So if you want to know why switching 2 phases reverses the motor, ask them. Them being electrical engineers and not me. So I just know what to do when it's going the wrong way. So I will, move 2 phases, bump it again, and then we're good to go. So then we're happy with the motors. We're not checking IO yet. We're just checking like that we can run motors. Then we'll check IO. So what's IO? Input, output. Like it's short for inputs and outputs. But they're talking about all the actual physical wiring, the interface, between the PLC and the real world are these IO cards. And the IO is really, all the field devices is called the IO. And they're normally, signal voltages are a lot lower than, power voltages needed to move, real stuff. Signals don't need to be super high voltage like that. So they're normally in different pipe. And they go to, some lower voltage control cabinets sometimes. If you you do separate those, and that is a typical practice to separate your control voltage and your power voltage into different cabinets. I see that all the time. But you can put them all in the same cabinet, and that's what UL 508A is for. Otherwise, you have a bunch of MCCs, which are motor control centers, and that's all high voltage stuff. And then you have another cabinet with all the low voltage control stuff inside of it. But anyway, IO checkout, continuing IO checkout. I just keep going off of tangents, sorry. So when you're done with IO checkout, that means that you checked every single input and output to the PLC. And you not just checked it, that like it's to the right one, because you can mix them up, right? Like let's say you have 3 valves. Well, maybe the input you thought was one valve is a different valve. So you fix all that, and now you know that everything's talking to, that the PLC is really talking to the real world the way it really believes it is. Like you're basically validating that code will really run because it's really hooked up to all those things that the PLC thinks that it's hooked up to. And you have to check, a change of, like for something that switches, something that's an on-off type thing. You need to check that it changes state. If you just have one or the other, you didn't really prove anything. So that's not part of IO checkout. You need to check that like every channel is really hooked up to the real device, and then check to see the health of that signal. So if it's an analog device, you should get it to move through its whatever range it is supposed to be able to move. If you have thermocouples, you're supposed to hold it and see if it increases in temperature, because if they're wired backwards, they actually will go down in temperature. Some of them will. But anyway, there's things that we go check so that we know, and then we're signing this too. We're saying, okay, I checked this channel, and there's someone on both ends, right? Because there's a PLC person checking in the PLC side, and then there's someone checking the field device, and then you're communicating with each other, and then you're signing off point by point that all of it, and I'm not talking about commissioning, I'm just talking about IO checkout. Once you have done all of that, then you can say that that you've done the IO checkout, and now you can do sequences, right? Now you can test that your code works, but first you have to test that like the PLC is hooked up properly to the real world. And that's what IO checkout is. And it is a 2-person job, and if anyone says otherwise, they're liars. A really good pairing for IO checkout is a programmer and like a mechanical person, or at least someone who wants to put on the harness, because they're going to get up in some weird spots. Because motors are not wired right. I've had motors wired wrong from the factory, so like we're hooked up right and they're not hooked up right to themselves. And so sometimes there's phone calls, right, to OEMs. You're like, what is this? Like, what is going on with your thing? And then you read them a serial number, and you read them stuff on there, and then they tell you what's going on. And then you learn from that, and then you're able to do that, super fast the next time you see it again. So IO checkout is not for the faint of heart. It is a struggle. You're the last one on the job site, so everyone's like, hurry up. Everybody's already finished their stuff, because controls is always last. Because we're actually we're going to start it and make it do the thing. And then hand it over, and that's the the last part of that after you commission it is training operators, and then just basically kind of supervising them until they feel like they're comfortable without you, and then when they're ready, they're like, okay, I can do this without you, go away, and then that's it, and then you go on to the next project, and maybe you design it and maybe you don't, but the startup is the same thing. And somebody needs to make that startup paperwork, and that's supposed to be the programmer, because who's ever doing all this PLC writing or PLC code writing should have had a real IO list or PNIDs or whatever to build their code off of, and then a narrative. That's what it's called. when you write down the description of what the code's supposed to do, they call it a functional narrative. Sometimes it's called a sequence of operations, but it's functional narrative or control narrative are two really common terms for just like a document that says in writing what the PLC is supposed to do. Things like if the level in the tank goes below some set point, interlock the pump so that it can't, run it dry. Just that's a written description of how to turn on and off bits and what you're looking for in the PLC. So that's called a control narrative or a functional narrative. And not just controls people write those. That's actually traditionally written by process or mechanical engineers telling, programmers what to write in there. So it is definitely very helpful if you were a designer of some sort, either process or mechanical, or, if you were a designer before you did, IO checkout, that's super helpful. But it's also helpful for troubleshooting. So I've now gone 11 minutes, which is wow. So that's what IO checkout is. It's verifying that the PLC is gonna work when you actually run your code, and that will be its own struggle. But you have to start with, okay, I know I'm hooked up good to all the IO. All the field devices are hooked up good, so now let's make it do the sequences correctly. And then once we're done, save it. They call it burn the EEPROM, which actually is just like an old term for like save it, to the memory, to the hard memory of the controller, which they all have now. They didn't all used to have that. Sometimes they would fault out and have no program, and your machine won't run because literally the PLC has no program to run. Like that is a normal old problem because of the way they did memory, and some of these PLCs are old. I did one a few years ago that had been going since 1998. So these things go, and they go and they go until they don't. That's it. I guess. Thanks for listening.